All right, so looking at these values here, again, I want to draw your attention to the top right-hand corner. Now, of course, the noble gases, you see xenon does have an electronegativity value here, and there's exceptions to every rule we give you. But what we're going to say about the noble gases is they have zero desire for electrons. Every atom wants 8 in the outer shell, in the valence shell. And noble gases, group 18, already have those 8 electrons, so they don't need to add any. So they don't want any additional electrons. They have no desire for electrons, so they have electronegativity values of 0. The same is true for the first group, the alkali metals, especially the bottom of the group. These have very little desire for electrons. In fact, they really want to give their electrons away. But think about group 17, the halogens. The halogens have 7 valence electrons. How many do they want total again? They want 8. They just need one more. So if you're just one away from completing what you want, you're probably going to work harder for it than if you were over here in group 1 and we're 7 away. So group 17, because they're so close to their 8, they really want that extra electron, so their electronegativity values are that much higher. Here's an image kind of showing what we're going to talk about next, and that's ionization energies. And ionization energy, if we look at the word, you can see the root word is ion. And this is one of those terms that you need to always remember, but oftentimes most students forget. Does anyone know what an ion is? So it's an atom with something. It's an atom that has a charge. That means it might be a positive ion or it might be a negative ion. A positive atom or a negative atom, those are charged atoms. We call those ions. Yeah, so it's exactly that. It comes down to the number of protons versus electrons. So to make something charged, you have to basically steal an electron or give it an electron. Well, ionization energy is the energy needed to take away an electron. And when we simply define it, it doesn't change much. It's pretty much the same definition. The energy required to remove one electron from a neutral atom. In other words, how much energy is needed to steal an atom's electron? Some atoms don't want to lose their electrons, so they will not let you steal the electrons from them. Again, everything we see about this has to deal with the number 8 and how every atom wants 8 valence electrons. So what group will not let you take a single electron from them? The noble gases. Group 18. Why will group 18 not let you take an electron? They have all 8. They're not going to risk losing one. They're complete. Now, group 1, as you know, just like in electronegativity, it has no desire to keep that one. It wants to get rid of it. So you could imagine it's really easy to come over to this atom and take this electron away. Very little energy is needed. In fact, they want to give it away. So it's going to be really easy to steal that electron. And then it's going to rely on the next shell that should be filled underneath. Now, of course, this first ring only fills with 2. Everything else fills with 8. But group 17 and group 18 especially, 18 has all 8 electrons, so it doesn't want to lose a single one of these, so it's very difficult to take from here. So noble gases have a very high ionization energy. Group 17 only needs one more. It would work perfectly if this one came here, and they kind of completed each other. Well, group 1 doesn't want it. Group 17 really wants it, and it really wants to hang on to what it has, so it also will have a high ionization energy. It's not going to be really easy to steal an electron from the groups on the right. So that means the noble gases have the highest energy needed. So energy here is really high. That means it takes a lot of energy to steal these electrons. But over here on this end, it doesn't take very much energy. The amount of energy needed is low. And then down here, it's especially even lower. So the reason it's higher to the right of the table on this end is because it's almost filled. It's so close to being filled, it just needs a few more electrons. So it doesn't want to lose any, it wants to gain more. So it's not going to allow you to steal electrons from it very easily. On the left, though, they're very close to having the shell below the outer ring filled. They have 1, 2, or 3 valence electrons. They're not going to gain 7 or 6 or 5. They'd rather just give what they have away, so they want to lose them. And then the ones going down here that show you this overall trend, the reason the ones lower have even a weaker desire for electrons and it's even easier to steal them is because if you think about how many rings this one has down here, this is in period 7. So this atom has 7 rings. It's an awful drawing. But if it has 7 rings and on that outer ring it has 1 electron, the nucleus of the atom, which is positive, has a very weak attraction for this negative because of something called shielding. There's all these electrons in between, right? 8 per ring. And I'm not going to draw that exact, but they kind of shield this outer electron from the positive nucleus. So the attraction is so weak between these two particles that it's real easy to come in and take that electron away. So basically, the more rings you have, it's like the more you have to take care of, the more you have to look out for. And it would be a lot easier for someone to steal from you if you had a lot of land to cover, a lot of area to cover to protect, than if you had very little area to protect. So that's why the lower the group, the lower the energy needed. When it comes to ionic radius, again, we're dealing with the size of an atom. There's no textbook definition here for you, but simply put, it's the size of an ion. And an ion, again, we said was a positively charged atom or a negatively charged atom. Well, this group 1 atom here has the 1 valence electron that it wants to lose. And, oh, sorry. Let's get this up. All right, let me delete this. All right, so ionic radius again is defined as the size of an ion, and an ion is either a positively charged atom or a negatively charged atom. In this case, this neutral atom lost an electron, so it became this one here. It's a smaller atom. So whenever it loses an electron, think of it like it's losing weight. It's losing mass, and it's going to become smaller. Whenever it loses an electron, it becomes positively charged. Now here what's happening is it gained this electron. So you can think of that as like gaining weight. So this anion, this negative version of the same atom, gained an electron, gained weight, gained mass, gained matter to its outer ring, and as a result, it's going to be even larger. So to sum it up, what we're going to see is a neutral atom kind of falls in the middle. The cation, which is the positive ion, will lose an electron and become smaller as it loses matter or mass, loses the number of rings that are occupied. But the anion, the negative ion, Because it gains electrons, you could kind of think of it as like gaining weight. It becomes larger because it's adding more matter or more mass, adding to that outer ring, making the atom itself take up a larger area. So from smallest to largest, the cation's the smallest, the neutral one's medium sized, and the anion's the largest. So again, we go small, medium, and large. And it all has to deal with whether it's gaining or losing electrons, and you can determine that by its charge. Positive means it lost weight, negative means it gained weight, positive means it shrunk, negative means it grew. So that concludes this video and these notes. I guess we're done.